So yeah, I'm presenting on behalf of our team of co-investigators. So that's Debashis Ghosh and Dinesh Mondal at the International Centre for Diarrheal Disease Research in Bangladesh, Dr. Russo Joaka at IITA in Benin in Cameroon, and my colleague at the University of Greenwich, Bob Cheek. So our research project was looking at exactly the question that Marianne was sort of addressing just there, whether or not we can use an alternative to the human landing catch for blackflies and sandflies. So the context here is that with neglected vectors, you need to perhaps be looking at how to collect actually quite a lot of insects in disease elimination context. So the successful interruption of transmission of diseases like onchocerciasis and leishmania, you need to kind of show that there's an absence of parasites in the vectors as well as people. And that's probably one of the most sensitive measures for the interruption of transmission of these neglected tropical diseases. So as we're very positively entering elimination stages for some of these diseases, we also need to be kind of upping our game in terms of vector surveillance rather than perhaps scaling back, which I think is a risk sometimes where we feel like we've made really good progress. So we can perhaps take our eye off the ball a little bit. We really need to be enhancing vector surveillance. But for some of these neglected vectors, the tools are things we've been using for a really long time, and they are not without problems. They aren't perhaps necessarily the most sensitive, and particularly where you have very, very low densities of vectors, it can be a real challenge to actually collect enough material, enough specimens to be able to make that verification of whether or not you have a very low percentage of infections still in that vector population. So our aim was to determine the efficacy of a new behaviour-based vector trap. It's called the host decoy trap, for the surveillance of adult Simulium and phlebotomus. So that's the blackflies and sandflies. So just as a brief introduction to the decoy trap, it's something that we've developed at the University of Greenwich for the outdoor surveillance of malaria mosquitoes. And we have very much a similar issue in that sphere that really for outdoor collections of outdoor biting mosquitoes, we don't have anything much better than a human landing catch. So we developed this tool. It's driven by behavioural research, so understanding about how the vector locates a human host to feed on. And some of those behaviours we're fairly confident are quite ubiquitous across the groups of blood-feeding insects. So the decoy trap combines these cues into a host mimic. It's kind of a supernormal stimulus to attract mosquitoes, and in our collections we've also found other blood-sucking insects as well, including blackflies and sandflies. So that gave us a little bit of an indication that it might be a suitable tool for these neglected vectors too. It's a sticky trap, so essentially we have a person sleeping in a tent, so we still use whole human odour. We're not trying to work on the chemical ecology here and identify attractive odour blends, although there are people working in these areas too. And then that odour is just, by a simple fan, blown towards what's essentially a bucket that's filled with warm water to maintain a surface temperature kind of close to human body temperature. And it's got high contrast visual stimuli as well. So just a plain solid background, and then it's covered in sticky plastic so the attracted insects land on it. And we've had very, very good results with outdoor biting malaria mosquitoes. So for blackfly sampling, we were working along the Mbam River in Cameroon, and this is an area dominated by Simulium danosum, which is the principal vector of onchocerciasis in this area. It's one of 5 hyperendemic onchofoci in Cameroon, and we here, because blackfly are day biting, we're doing experiments during the day. And we're comparing the host decoy trap to the human landing catch, as well as the Esperanza window trap, which is one of the standards that's used in blackfly surveillance. And that's been supplemented with CO2, so it has a sort of visual and olfactory component to it. And then for sandfly sampling, we were working in Trishul, which is near Mymensingh in Bangladesh. It's highly endemic for visceral leishmaniasis, but has been quite successful thanks to the national elimination programme to reducing the incidence there quite significantly, but still does remain a problem in the area. Here, again, slightly different because sandflies are obviously nocturnal species in terms of their host-seeking behaviour. So we were doing experiments during the night. Again, comparing to a standard human landing catch, but also comparing to the CDC light trap, which is more commonly used for sandfly sampling. So all of our field work happened in October and November last year. It had been due to happen a lot sooner than that. In Cameroon, we were due to start at the beginning of 2020, but there was a kind of snap election, which made that slightly risky for travel. So we postponed it, and unfortunately, COVID got in the way, and likewise with our planned field work for Bangladesh. So we took a pause, and we're very grateful for the extension that we were given to allow us to carry out that field work slightly later in the year. Bob and I had been due to travel, which obviously didn't happen. So all of our work kind of happened remotely, with the field teams kind of receiving and being really good at taking sort of remote guidance. And I'm really grateful for how much they made me feel part of the research process, even though it was completely remote. So here's just how we used WhatsApp. I mean, it became a really great way for us to communicate as though we were in the field with each other. It was great. So Debashis sent some photos of potential study locations, so we could kind of discuss in the fields whilst he was there where might or might not be most suitable. And here's a video that Rousseau sent to show some of the training for the human landing catch collections and how to use the aspirator correctly and quickly to prevent getting bitten by blackflies. So we kind of had to just do this really entirely remotely, which with new technologies and new techniques, you really have to get that right, because it's hard to otherwise distinguish if maybe things don't work. Is it because some simple step has been missed, or your protocol isn't quite as robust as you thought it was? So we couldn't replace being there in person, but we gave a good shot for using WhatsApp and things like this to help that happen. So on to our results for blackflies first. So over the course of the fieldwork, we caught, which was only 9 nights, which doesn't seem like very much, but we have really high numbers of flies around at that time of year. And based on our power calculations, we were confident we'd be able to see any significant differences, and we were. In total, we caught 8,351 female blackflies over the course of those 9 nights of experimental data collection, all with a Latin square experimental design. These were identified to the Simelian squamosum of the Damnosum complex by morphology. We had planned to do cytotaxonomy, but we couldn't do that under the COVID situation. But we know from this area that squamosum B and E2 are found in the Mbam River. We also know that there's Simelium mangensi in the area in very low numbers, but we didn't catch any of those at all in the collections. And you can see from the figure here that we actually had really quite dramatic and encouraging results for blackfly. So both the host decoy trap and the human landing catch caught significantly more squamosum than the Esperanza window trap by quite some way. So just for an example, the HDT, the decoy trap, was catching about 500-600 blackfly a day, whilst the Esperanza window trap was only catching about 9 or 10. So an order of magnitude and then some in difference. The decoy trap did catch more than the human landing catch, but not a significant difference. So we're really encouraged by those results. We can look into that a little bit more detail as well, because with mosquitoes, we found that the decoy trap at high densities remains really, really efficient, whereas a human collector tails off. Their ability to keep up with the sheer number of insects landing kind of falls away. And we see something similar here with blackfly. So there's a density dependent effect that we've observed. Around about up to about 400 flies per person per day, we can see that the human landing catch and decoy trap are in fairly good accord, quite similar. But after about 400 flies, we think that the human collector really just can't keep up with the number of flies that are landing, either because there are multiple flies landing at the same time, or they just miss individuals that are landing on their bodies to be collected. So as with mosquitoes, we think that actually some of these human landing catches, even though they are the gold standard, where you have a very high vector abundance, might be quite significantly underestimating the biting rate, which in some contexts could explain where we have a higher transmission rate than we might have estimated from the vector data, from the ENTO data. And we dissected, I say we, the team in Cameroon, very valiantly took these black flies off the sticky traps and went through dissections with them. We couldn't get the reagents to the field to do anything other than dissections, but it was really valuable to know that as a kind of fallback, we were able to do that with samples from the decoy trap. We obviously by dissection couldn't differentiate between Onchocerca ochengi and volvulus, but nonetheless we did find L3 stage larvae in the decoy trap. So we had at least one infected fly from the decoy trap, although we didn't find any in the human landing catch subsample that we dissected. For the sandfly results, in total we caught 147 sandflies. These were predominantly Phlebotomus argentipes, so about 77% argentipes, and then the remainder were of the Sargentomyia species. Males accounted for well over half of the total catch. So unlike blackflies and most Anopheles malaria mosquitoes, male sandflies are attracted to the host for the purpose of finding females whilst they're searching for a blood meal. So we, this is the first time we've kind of been able to demonstrate that this trap, which is normally only going to be attractive to an insect that's actually looking for a blood meal, it might also be attractive to other fractions of that population who are looking for a female to mate with whilst that female is host seeking. So that was a nice find. We used RPA to see if we could find any parasite positive samples in the argentipes that we collected, but in this occasion, and with not very many sandflies, it's perhaps no surprise that we didn't find any positive for Leishmania donovani. In terms of the trap results for sandflies, the human decoy trap, the host decoy trap, did not work particularly well, which is quite interesting, and it does go to show that you can't necessarily just translate one behaviour between a blood-seeking insect and another from a completely different group. Although it may be how we use the decoy trap in terms of its location. So we used it outside exactly as we would with the black flies and with mosquitoes. And of course, sandflies are quite often associated with an indoor environment. So perhaps this might have had a slightly different outcome if we'd put the trap inside where the CDC light trap had been positioned as well. So, but it does also show that the CDC light trap is still relatively good as a comparator to the human landing catch in this case. We've also got here the mean nightly catch of mosquitoes. So our colleagues also collected the mosquitoes at the same time as they were collecting sandflies, not deliberately. This is just it's a trap that's going to attract mosquitoes too. And you can see that the decoy trap is catching a huge number of mosquitoes. So we were sure that the trap was working correctly, which for a remote fieldwork situation was quite nice to be able to validate it that way. So we know that there was nothing wrong with how the trap was operating because it had such a high capture rate for mosquitoes too. One thing that's worth noting is that in the CDC light trap, we had a really large bycatch of other insects, so other nocturnal species like moths and things like this, but we didn't have any bycatch in the decoy trap or the human landing catch. And I think that's probably quite an important point for consideration going forward in terms of which traps you might consider to be acceptable. So just to summarise then, the host decoy traps could be quite a valuable tool in Blackfly surveillance for elimination contexts. I think John mentioned earlier, a couple of other people have alluded to the fact you need to have thousands of flies screened and verified as negative for parasites. And to actually collect those numbers of flies with a human host is not the easiest thing to do in the world. So having something that's standardized, completely safe, so that the collector's not exposed to infected bites, it is really promising. And now we're talking to site savers about the potential for exploring how this tool might be used in other areas outside of Cameroon, but within West Africa, where we're looking at elimination. And again, that point about having a bycatch, you don't really want to be catching hundreds or thousands of potentially beneficial insects at the same time. So there's another dimension to making sure your trap is targeted. Clearly, it didn't work so well for sandflies, and it may be that that was to do with how we positioned the trap, which can make a huge difference in your collections. We didn't find any significant difference between the different areas that we trapped, but just that difference between indoor and outdoor collections might be important. And really, the final point I'd like to make is that we really do need to study some of the fundamental behaviours of these neglected vectors. I think that's really, really important, because with that information, we can then make much more targeted tools that have a much greater chance of success in the field. So finally, a big thank you to the Gnatwork and the Gnatwork team, of course, and the funders at BBSRC who support the Gnatwork and us indirectly, as well as Peter Enyong and Armand, who did a lot of the field collections in Cameroon under quite difficult conditions, and our partner Martin Geyer at Biogents, who has helped us develop a commercial prototype of the decoy trap. There is a protocol for the trap available on the Gnatwork website. So thank you very much.